Hello, AP Bio. It's Mrs. Ness-Deden, and today we are going to analyze some data about M&Ms. You know how everybody's got a favorite color of M&M, and when you open up the package, there's just this nice mixture that just really makes you want more M&Ms. Do you know there are people whose entire job it is to figure out like the perfect color combination that makes you want to keep eating more M&Ms? They're called customer satisfaction psychologists. Apparently that's a thing. And apparently the people at the company that makes M&Ms, which is the Mars company, have actually researched this. And this is kind of what they present as the perfect blend of colors to make you want to keep grabbing those handfuls of little chocolate goodies. The M&Ms that we gathered data on were plain M&Ms, and so according to Mars Company, these are the percentages of colors that we should have seen in that sample. Well, many of you ate some M&Ms and gathered some data on this for us over the last couple days. And so what we really want to find out is whether the M&Ms that we looked at fit this expected data, fit what the Mars Company says we should find in terms of colors. And so what we're going to learn today is the chi-square test. This is a statistical test that's sometimes called a goodness of fit test, looking at how well our data fits these expected percentages. Obviously, because it's real life, things aren't going to be absolutely perfect. You're not going to get exactly these percentages in every package. But what a chi-square test can tell us is whether the differences that we see are just due to chance, or if something's actually wrong, a machine's broken at the M&M factory or something else like that's going on that's actually kind of skewing the data. Whenever we do a chi-square test, we start with what is called the null hypothesis. The word null means nothing. And so the null hypothesis is always the hypothesis that nothing's actually going on. It's just random chance. This is always part of any experiment that you do as well. The null hypothesis is just that idea that whatever you are doing does not actually make a difference. You can also kind of think of this, if you read this little thing on the screen, kind of think of this like innocent until proven guilty. We assume that any differences we see are due to chance unless we can prove otherwise using statistics. So when you write a null hypothesis, this is kind of the template you should use. Like any statistical test, there's certain language that goes along with this that you kind of just have to learn and memorize, because these are the words that I will be looking for and the people who grade the AP exam will be looking for anytime that you do a chi-square test. So the template to use for a null hypothesis is like this. I predict there will be no statistically significant difference between whatever you're observing and whatever you're expecting. Don't just put the words observed and expected in there, though. Describe what they actually are. So if we were to write a null hypothesis for our M&M lab, it would look something like this. I predict there will be no statistically significant difference between the colors counted in our class M&Ms, that's what we actually observed, and the percentages provided by Mars Company. That's the expected values that you see in this table up at the top of the screen. So the point of a chi-square test is to test this hypothesis to see whether or not there actually is a statistically significant difference. This is the formula for chi-square. This is on your equations and formula sheet, and it explains what all the variables mean. So there's lots of information on there. And so what you can see here is we take the difference between what we observe and what we expect, square that difference, divide it by the expected. We do that for every single category of values that we're working with, and then we take the sum of them. One important thing to note is that, first of all, chi is actually like a fancy X that has like a swirly side there. And also, we are trying to find chi-square. We do not solve for the X in this equation. You never take the square root of this. You're just solving for chi-square. So you just do this calculation on the right, and that is your chi-square value. Notice a couple things about this. First of all, if observed and expected are equal, what would your chi-square value be? If those two are the same, you're going to end up with 0, right? Which means there's 0 difference between what you observe and what you expect. Obviously, in real life, that's very rare, but that would mean that there's absolutely no difference. We are seeing exactly what we expected to see. And then also notice what happens as the observed and expected values get farther apart. In that case, the chi-square value is going to get bigger and bigger. And so obviously a small chi-square value is going to tell us that there's just a little difference, which maybe we can attribute to chance or random mistakes. But the bigger that difference gets, the less likely it is that that's only due to chance. So the bigger a chi-square value is, the more likely it is that something is actually going on that's not just random chance. So this is how we're going to calculate our chi-square value for our M&M data. This table is a tool that will be given to you the first few times that you calculate a chi-square value. There are some practice problems posted in Classroom today that give you this chart to work with. The fruit fly lab that you analyze will also give you this chart to help you kind of work through. But basically all this does is it walks you through step by step. List your observed values, list your expected values, and then it just walks you through doing the calculation. First, we're going to calculate the difference, take observed minus expected, then we're going to square that difference, then we're going to divide it by the expected, and then we're going to add them all up. So it's just walking you through the calculation step by step. It is important to note that on the AP exam, they will not give you a nice pretty chart like this, that you will just have the equation. So eventually you do want to practice some of these calculations, and we will practice some of these calculations without having this chart created for you. You can always draw one yourself if you find it helpful, but that won't be given to you. So these are our observed values. This is data that was collected by students in the classes when you actually counted some M&Ms. To find the expected values, we have to use those percentages that were given. But when you're calculating a chi-square value, you can't use percentages. You have to calculate the actual numbers. So if we add up all the M&Ms we counted, we had a total of 619 M&Ms. So now we can take that 619 and figure out, okay, what would 13% of 619 be? What would 20% of 619 be? And that's how we find our expected values, which you can see right there. So the expected values here are the total amount of M&Ms times the percent that we expected according to the Mars company. That's how we find our expected values in this case. The next step is to subtract the observed minus the expected. So in each column, we're just taking the top number minus the next number. And so if we go through and do that calculation, some of them will be negative, some of them will be positive. It actually doesn't really matter because the next thing is you take observed minus expected and you square it. And anytime you square something, you're going to end up with all positive numbers. So if we square all of the numbers in this row, we get this next set of values right here. So this is the observed minus expected squared for each of our M&M colors. And then we divide that number by the expected value. So here we're doing 2.16 divided by 80.47, which gives us 0.027. And we did that all across the row. And the very last step is to sum up, just add up all the values in this very last row to get our actual chi-square value, which you see down here in the bottom corner. In this case, our calculated chi-square value is 17.234. Okay, so now we have a number. What does that number mean? There are a couple more steps to figuring out exactly what a chi-square number means once you've calculated that value. In addition to the equation on your equation sheet, you will also see a chart of values that has a couple of things on there. One of them is a number called the degrees of freedom. We already know that the larger our chi-square number, the bigger the difference, but we still need to figure out kind of where is the cutoff of when that difference actually becomes statistically significant as opposed to just being due to random chance. One of the things that is a part of that consideration is something called the degrees of freedom. One way to think about what this means is how many ways could you possibly be wrong? And here's kind of what I mean by that. If you flip a coin and you guess what the answer is going to be, you guess that it's going to be heads. How many ways could you be wrong? Just one, right? If you guess heads, it could be tails. There's one way that you could be wrong. If you have a bunch of M&Ms and you pick out one M&M and you say, I think I'm going to grab a red M&M, there's a lot more ways you could be wrong, right? It could be orange, yellow, green, blue, or brown. There's like 5 ways that you could be wrong. So the degrees of freedom is kind of how many different ways that you could be incorrect, how many other choices there are. And hopefully it makes sense to you that the more degrees of freedom there are, the more natural variation we're going to expect. And so there's a higher chance that some of this difference is just due to chance. We're going to have more differences when there's more colors to choose from. The degrees of freedom is included on your equation sheet as well. It's the number of categories or groupings that you have minus 1. So think about that for your M&Ms. What would our degrees of freedom number be for our M&Ms? In this case, we have 1, 2, 3, 4, 5, 6 categories. 6 minus 1, we have 5 degrees of freedom in this particular case. That's important because on your equation sheet, like I mentioned, there is this little chart. And you can see that there are a couple of things on here. And one of the things, the top row up here, lists the degrees of freedom. And right here, we just said that we have 5 degrees of freedom in this particular example. You'll also see that there are 2 rows on here that list the p-value. P has to do with probability. And in AP Bio, we always use the 0.05 row unless it specifically tells you different. They print both of them on the equation sheet, but you just always need to look at this one unless it tells you differently. And the reason we use that is similar to when we were talking about standard error of the mean. In science, we like to speak with 95% confidence. That's just kind of a generally accepted confidence level in terms of statistics. And that 0.05 is another way of saying there is less than a 5% chance that this is only due to random error. So what this gives us is kind of the cutoff value, the value at the intersection here. In our case, this number for this particular problem, 11.07, kind of gives us the cutoff number. Statisticians have done tons of calculations. There are actually charts that are much bigger than this, giving this type of information for chi-square calculations, but this is basically the cutoff value that we call the critical value, that shows us what level of difference we can accept as due to random chance. And so with that critical value of 11.07, now we can actually look at our chi-square value. If our chi-square value, so this, I'm just going to highlight that again, this 11.07 is kind of our cutoff value. If our chi-square value is lower than that, remember a lower number means there's less difference between what we observed and what we expected. So if our number is less than that, then we say the difference is not statistically significant. In other words, it is just due to random chance, so we accept the null hypothesis. We say, yes, there's nothing going on here. This was just due to random chance. However, if our chi-square value is bigger than the number that we see in that box, we reject the null, which is a little bit of a confusing phrase because it means it's not nothing. We're saying this isn't just due to random chance. There's something else going on. And at that point, we need to come up with an alternate hypothesis, a different explanation for this. So, of course, you need the language to say this with. When we're going to write this kind of analysis of our chi-square test, this is the phrasing that you can use. I accept or reject, depending on the number, my null hypothesis because the chi-square value of this number is lower or higher than the critical value. So all of these things that are written kind of in brackets like this, you need to look at your value and look at the critical value and first decide, are you accepting or rejecting? And then you need to fill in the appropriate information for all of this. See if you can write what our analysis would be for our chi-square value here. Hopefully you wrote something like this. We should reject our null hypothesis because the chi-square value of 17.234 is higher than the critical value of 11.07 for p equals 0.05 at 5 degrees of freedom. So you have all the information in there. And by rejecting the null hypothesis, remember, we're saying this is not nothing. There's something going on. So if this was an actual kind of science lab, then you would need to go on and say, this means the difference is not due to random chance and could be explained by an alternate hypothesis. And then you can kind of propose what you think that might be. Perhaps a worker at the factory had a kid who really likes yellow and green M&Ms. Or perhaps the brown M&M machine was broken that day, or whatever it might be. Then you go on to propose and kind of scientifically explain what you think might be happening. So here are the things that you need to do next. I have attached a worksheet with 3 practice problems if you want to just try out this chi-square thing and make sure that you're on the right track with this before you go to do your fruit fly lab. I will add a key for that during the day on Wednesday. My key is at school, and so I have to scan that in, and I will attach it to the classroom post tomorrow. And then once you feel confident with chi-square, you can begin working on the fruit fly post lab, which is also attached to today's classroom post. It will be due next Wednesday, so you do have a few days. Please make sure that you start working on it. So if you have any questions about how to apply this chi-square stuff to our fruit fly lab, you have enough time to ask. You'll be calculating the chi-square value for each trial that you ran in your experiment. So most of you will be doing this 3 or 4 or 5 times. And that will help you determine whether or not the flies were evenly distributed. That would kind of be your null hypothesis. And whether the differences you saw were just due to chance or whether they were actually showing a preference for one end of the choice chamber or the other. So go and do some practice. Shoot me an email with any questions that you might have. And I hope you enjoy your nice, lovely, long weekend.